This video will discuss question 11, which goes as follows. Disregarding the limiter circuit, what are the locations of the closed loop poles S1 and S2? These are in fact the values of S for which the open loop gain beta A is 1. Now to solve that question, we should first find an analytic expression for beta. So let's do that. The feedback network looks like this. We have two series components, a resistor and a capacitor, and two parallel components, another resistor and capacitor of the same value. To simplify our expressions later on, we will describe these two components as ZS for series impedance and these two components as ZP for parallel components. If we then want to find an expression for beta, it will be just as simple as using voltage division like this. ZP over ZP plus ZS. To simplify this expression, we can now divide both the numerator and the denominator by ZP. Now we have a vague form of how beta should look. We can go back to the main question, which is how to find the closed loop poles. Finding the closed loop poles is equivalent to solving the expression A beta S is 1, which means we could also solve it as A is 1 over beta S. Filling in the equation that we got here, we can say that A has to be equal to 1 plus ZS YP. Since the value of A is still unknown, let's find that one first. A is the gain of our non-inverting amplifier in the circuit, and we can find the numerical value of it by filling in the equation 1 plus R2 over R1. R2 is the feedback resistor and R1 is the resistor that goes to ground. If we fill in the values that have been given to us, we'll get 1 plus 20.3 kiloohms over 10 kiloohms. That's the same as 3.03. Now we can write out the full equation. That'll be 3.03 is 1 plus R, which is the resistance in the series path, plus 1 over SC times 1 over R, which is the conductance in the parallel path, plus SC, which is the admittance of the capacitor in the parallel path. If we now simplify this equation into the easiest form, we'll get the following equation. Since this equation is just a simple quadratic equation, we can solve this with a generic technique like the quadratic formula, and that'll give us the values of the closed loop poles, which are 93.75 plus or minus J 6250.